So, very welcome to this seminar, and you may take your seats or find a seat somewhere. Early on, when we were planning this conference, and in the beginning there were so few that had confirmed their participation, so we thought it's nice to sit around tables, and then all of a sudden it was like 80 people, but we still think it's nice to sit around tables, because then you can chat about what you hear in between presentations. Very welcome here. My name is Åsa Burman, and I will be the moderator of this seminar. And I work as a director of Lighthouse, the Swedish collaboration platform for maritime research and innovation. And we are arranging this seminar today. There are no evacuation tests today, meaning if there is a fire alarm, we go out and we meet at Kuggen, this multicolored building out there. And I do hope it works better than when we actually had a drill, because we had that last week. And everybody went out, because we didn't even know it was a drill. So we went out and we stood there, and then they said, now it's okay to go in again. And when we went in, all the loudspeakers started saying, there's a fire in the building, you have to leave, you have to leave. So in shipping you would never do such a bad test that we did. Anyway, a few words about Lighthouse for those, and I see there are many new faces here. Very glad to see them. And this is the program of today, and I think on the paper it says we should end at 14:45. I don't think we will, because that's not how we planned it, but I did not make sure that we had changed the date. So I hope you can stay until 3 o'clock, and afterwards mingle and have some coffee and whatever, fika, Swedish, served outside. So we will have 3 themes: research, rules and regulations, development, and innovation in industry. And a few words about Lighthouse. What is Lighthouse? Well, we say we're the Swedish platform for collaboration and knowledge exchange in maritime research and innovation. And we have been active as a platform for collaboration now for 10 years. And these are our partners and members. And others are welcome to join. Sven, for instance, keeps asking how to become a member, but you need to say yes to our proposals as well. We focus on sustainable shipping in all aspects, and we're interdisciplinary. So we work with maritime law, we work with hull performance, hydrodynamics, working environment, energy, environment, whatever. All of these things that actually are connected to the shipping sector. And we do this by, we have 3 different tasks: creating collaboration and networking. This is an example of creating collaboration and networking. We do seminars, we do workshops, we have pre-studies, and we have projects. And we also have focus groups. And for those of you who don't know, we have focus groups on fossil-free shipping, smart ships, and ports. And it's free to join. Most of the meetings are online. And we talk about what is happening, about project, about results, and also try to connect people together. So if you're interested in joining, you can just send me an email. We have a trainee program that we're running for the maritime sector, and I think we have at least 1, maybe more, trainees or former trainees in here. I saw you, yes, so I know. And then we have the sustainable shipping. It's a program, an industry program that Trafikverket has, the Swedish Transport Administration. They've actually procured it, and we did win that competition. And it's for 10 years, so we have a lot of projects running in that program. And I think you will see some of the results from these projects today. And then also matchmaking. I mean, it is if you have a question and if you don't know who to ask, you can always send an email to us and we will try to connect you to somebody who knows. It can be a researcher, it can be a company that works with what you're interested in. So we also work, when we say we work for increased R&I investments, it's like we inform the authorities and governmental agencies that there's a lot of need in the maritime industry, but there's a lot of challenges, but also a lot of opportunities. So could you please put some more money into this section? So, and that is actually, I mean, there are not so much money, but it's more than when we started 10 years ago. Communication and external monitoring is something that we do a lot also. Try to keep up with regulations, what is happening, what is discussed, what is coming. Are there any new reports? And of course, this is almost always global, because the international news are much. There's a lot of shipping news in international media. Not so much in Sweden, except for Sjöfartstidningen, who are actually here today. So that's a little about what we do at Lighthouse. And I have two colleagues, and you all met Caroline. She's a little pregnant and will be... she's very pregnant, actually. So she will we will have a replacer for her starting next week, and Caroline will go home for parental leave in January. And then we also have Lasse sitting in the back. He's our communications manager. And that leads us to the first presentation. And it will be by Sofia Werner, who works at RISE, Research Institutes of Sweden. And Sofia is a naval architect from DTU, has worked at SSPA RISE since 2007 as a researcher and project manager, and is responsible for hydrodynamics and wind propulsion. And Sofia will give the first introduction to the topic of today, a presentation with the title Wind Propulsion for Ships, New Opportunities and New Challenges. Welcome, Sofia. We hope it works.
Okay, thank you. Thank you very much, Åsa. Thank you for inviting me here. Always happy to talk about wind propulsion. It's actually my favorite subject. So, is wind propulsion the silver bullet to solve the climate change for shipping and reach the climate goals? No, it's not. Of course, there are many solutions to decarbonize shipping, and wind propulsion is just one of them. And it's not even the right solution for all cases and for all routes. So in this picture you see some numbers here. It's a bunker saving potential by fitting six flattened rotors on a VLCC on different routes. And if you compare the numbers here on the blue route, which is very windy, to the green route, which is operating in a not windy area, you see there's really large difference in saving. So for the green route, we would say wind propulsion is maybe not the right answer for you. So I start with a negative message that wind propulsion is not the right solution for every case. But having said that, of course, there are many merits. It's a technology that is available today, and we don't need any new infrastructure in the ports and so on for bunkering. It's a free source of energy, and it's predictable. And that's maybe surprising for some of you when I say that wind energy source is predictable. Here I show the average wind speed month by month for some years. And of course it varies up and down. We have some highs in the winter and lows in the summer. So up and down 10% over a year. And on top of that, here is the bunker price. And you can see for yourself which one you think is more predictable. So to give you a short technology overview of the techniques that we have on the market today. So probably many of you have heard these words. We have rotor sails, suction sails, and wing sails. These are the most dominating technologies today. Soft sails are mainly applied on yachts and large yachts, and kites is a few examples of kites exist. But mainly it's the rotor sails, suction sails, and wing sails that are dominating the market. Here we see the number of installations. These numbers are a bit old, but we can still see that the rotor sails and suction sails are still the dominating. All in all, we have now heard the latest number, I think 53 vessels, cargo vessels with wind propulsion out on the water today. So that's a lot compared to a few years ago when we had one or two, but still, of course, it's only a fraction of the world fleet. So to see the number of installations that we have installed today worldwide, we need a magnifier here, but there are some predictions, not made by me or by us, but from UK Clean Maritime Plan and from EU. So they predict that there will be up to 10,000 installations already in 2030 and 40,000 installations up to 2050. If this is true or not, I mean, nobody knows, but for sure both me and many with me believe that we are really in this takeoff of the curve now between the pink and the yellow area. We started slowly with some slow progress with the early adopters and the brave ship owners, but now we see many more questions from what can I say, mainstream ship owners, and at least we at RISE we get a lot of questions from ship owners, shipping companies on wind propulsion now. So we believe that we are starting to approaching this steep area of the innovation curve. So I'm from RISE, Research Institute of Sweden. It's owned by the government and independent institute doing both research and service to the industry. So I will in this presentation talk a little bit about how we as a research institute can support this industry and the development of this new industry. So our activities are divided on research projects where we receive national and EU funding, as well as projects where we directly try to support the industry so that they can take the right decision. So in general, our role is mainly as an independent third party, where we can be the link between ship owners and manufacturers, and to provide the trust to these new technologies. Lately, also some Asian shipyards start to be interested in this, and we have the research projects. So this is a way where we can link the research and innovation into the industry and link that with ship owners and makers. And then we have another dimension here, and that's standards and recommended procedures that is required for this in this new industry where everything is new to everyone. So we are also engaged in something called ITTC, International Towing Tank Conference. It's an organization of towing tanks worldwide that, for example, write recommended procedures and guidelines on various topics. And since the last 3 years, there's been a specialist committee for wind power and wind-assisted ships, which I'm chairing, and there are members from Asia and Europe. And yeah, this year we published 2 guidelines and recommended procedures, one for sea trials and one for power prediction for wind-assisted ships. So these are now published, and we will continue another 3 years to refine these guidelines and especially look into uncertainty assessments of them. And in this work we receive very good support from Trafikverket to look into the uncertainty assessments, which is very important. Okay, so the rest of the presentation I will try to give some example of more concrete work that we do. And I will cover these 4 topics here, and we start with performance assessments. So the most common question that we get, of course, both from industry and from students and journalists and so on, is always how much can we save and which system is the best? That's a natural question. And how can we compare apples to apples? So, as I said, we have now in ITC developed some guidelines on how to do the performance assessment, but there are still many ways to do this. There's many equations and different ways to do the comparison, and really to really make a fair comparison, apple to apple, we need to use the same computational tool when we compare technologies. So, for example, we at RISE, we have developed a tool we call Seaman Winds. There are many other organizations, universities and so on, they have their own tool that can do the same thing. But really the important thing is when we compare devices, we have to use the same tool and not take results from 3 different sources or organizations. Inside such a tool, for us and probably the same for all the others with this kind of tools, is that it's 2 steps. It's a performance prediction program and a voyage simulation. So these 2 components is required, and these 2 in combination gives a fuel saving en route, and that's really the performance KPI that we use, or power or energy saving on a route. So not the fuel saving on a particular wind or a particular day, but we have to take the average weather on a route covering both winter and summer and so on. Inside such a program there are many small modules. It looks complicated and I will not go through it in detail. But the trick is to be able to use such a tool at different levels of complexity throughout the project. So when we start in the early phase with a market scan, we only use like database sources from previous projects and so on. Then as we continue in the project phase, we can add more and more complexity to the calculations. And in the design phase, we can use, of course, all the big guns that we have. And finally, end up with a sea trial where we can compare with a prediction. So just to give you one example of what can be a difference between these steps, I will mention here the assessment of the forces from a Flettner rotor. In the first stage, we just model the rotor standing on the floor as a single object, and we get some thrust force, for example. In the next step, we put the same rotor on a ship and conduct CFD simulation for the same rotor. And here you see that the flow pattern is actually quite different now. When we put the same rotor on the ship, you see this blue area is the suction area, which provides the force, and it is much smaller now when we put it on the ship deck due to the disturbance of the hull. This is something that we still need to study more and do more research on, and here we have good help from a research project called Interact from Trafikverket. Another important aspect to consider here in the performance assessment stage is interaction between wings or between rotors that we should not forget. And the best way to assess this is, of course, with CFD. The problem is that it's really heavy computations. It takes thousands of CPU hours, and it's difficult to use this tool in a design stage covering all the wind directions, all sheet angles, and so on. So for that reason, we have spent a lot of time and effort to derive also low fidelity methods using a combination of RANs and lifting line to develop hybrid methods, which we also validated in wind tunnel in Southampton. Here you see the wind tunnel test with 3 wing sails on a row, really to see the interaction between them. Each wing here is almost one meter tall, so it was quite big wings. Here we got really great support from Energimyndigheten in 2 different projects to develop these methods and do the validation. But fuel saving is not only a technical question, so it's not only a question for me, but also for other experts. And I explain what I mean by that with this example from another project. Here we see the fuel consumption curve for different speeds for a given vessel without wind propulsion and with wind propulsion. So in this example here, for example, at 60 knot, we could decrease the power of fuel consumption by 20%, roughly. Now, if we add weather routing on top of this, we can lower the fuel consumption considerably more. So the weather routing has really a huge effect here. If we look at 10 knots instead, the percentage number change a lot, and we have here 60%. Now, if we also on top of this say that we have a flexible arrival time, we can be more flexible when we use engine or not. We can lower the curve even more. So with this example, I want to show that the saving numbers that we hear is not only just a technical question. It's not only looking at this ship, what will this ship give, or this wing solution, rotor solution, what will it give. The number depends completely on how we will operate. So we will use the weather routing, the speed, logistic requirements. So that's why crew and cargo owners are also key players, and not only naval architects. Okay, so that was a performance assessment. I move into maneuverability. Here it's important to look at the yaw balance. That's more important for projects with wind propulsion than conventional projects. Because both the rotor sails or wing sails, they produce, of course, the thrust force. That's what they are meant to do, but also side force. That makes the ship to have a drift angle, but there will also be a yaw moment, which you need to balance with a rudder. This yaw moment and yaw balance, it depends. It's affected a lot by the position of the wing sail or the rotor sail on the ship. So that's why it's very important to analyze this at an early design stage. Before it becomes, I mean, if we continue too far in the design and discover this problem late, it will be quite expensive to do changes. Here I will give one example that illustrates this. So here we have a normal ship without wind propulsion. We do a time domain simulation here, a collision avoidance maneuver. The ship discovers this small fishing vessel and do avoidance maneuver and come back to course. So this is acceptable. Now we add this flattener rotor on this fictive ship and try to repeat the simulation. And here the ship cannot come back to the original heading because the rudder angle was too large initial for just to keep the course. Now we can do two things. We can either move this rotor more forward or increase the rudder area. And we try again, and we see that now it's acceptable again. This kind of studies is fairly quick and easy to do at an early design stage, and we found that it's really useful to find problems and contract it at this design. Now we can of course also add waves to this. This is from a tool called Shipflow Motions. And you see the light blue or the colored arrows on the wing sails here. That's corresponding to the force that the wing sails generate. And we can see that the force change actually when the ship moves in the waves. So the ship motions change the forces on the wing sails, but also the wing sails change the ship motions because it adds aerodynamic damping to the ship. So this interacting effects is also quite interesting to study. And so these kind of simulations can be very useful for checking the control systems and also assessing loads for structural fatigue loads and so on. Good. We move on to sea trials and how to verify the performance in operation in real life. So we received this question back in 2020 to verify the performance of these 5 vessels in an EU research project, and there was no procedure at that time to how to do such a sea trial. So we had to derive a sea trial procedure, and that we then brought into the ITTC committee, and that then ended up to be the procedure that is now published. Very short how this works. It's simply on-off runs, short runs with a wind propulsion device on and off in minimum 5 wind directions. We measure the speed, engine power, and the wind, and from that we can work out see if the power saving prediction was correct or as expected. Here's some examples, and you see there's some scatter in the results, of course, but this is full-scale measurements, but at least it gives some indication of the savings. This procedure describes how we can do this both in short trial and as well as long-term campaigns. So if it's a short trial, 5 days, 5 points, it takes 1 day to conduct. It just gives a spot check of the polar. But then, of course, we can continue for weeks or months and gather more and more data, and we can see how it corresponds to the prediction. Okay, final subject here: operational aspects. These vessels, as all vessels, have various control systems. But maybe even more important now for power wind assisted ships is that the control systems work well together, especially the wing control or the rotor control system works with the sensors and the propeller engine, so on, to make these kind of ships work most optimal way. One problem is that there are probably different companies, organizations providing all these devices. So one company provides the wings, another the propeller. And they have their control systems with IP rights and so on. And how can we make sure that they work well together? So here we have developed what we call a co-simulation platform, working with FMI, so that all these organizations can plug in their control system to one common platform and make sure that they work properly together. And this is something we work with in a project from Hållbar Sjöfart called Virtual Windship. Another topic, sail trimming, and I think Olis will talk more about that later. But just as on a normal sailing boat, the sail or the wing is to be adjusted to the wind direction to work in the best way. But then, of course, we need to know what the wind direction is in every instant. So the question is, should we measure the wind, for example, here in a mast on the ship? Or should we try to measure it ahead of the ship so that we are prepared for a wind ship? These wing sails are quite slow to rotate. So if we get some heads up a few minutes before the wind shift, we could operate these ships more efficient. This could, for example, be done with a LiDAR to spot the wind shift ahead. And here we have just started a project called Wind Spotter, also from Hållbar Sjöfart, where we will look into the possibility to use LiDAR to spot the wind shift before they come, and be prepared for the wind shift. Finally, a few words about the crew. This new technology will require some control panels. And how should these control panels be designed so that the crew can operate it in the best way? And what information do they want to see? To test this, we have had some sessions in our simulator with the real captains to try out different designs on control panels, see how they interpret them, how they can understand it, how easy it is to operate. And this has been a really useful feedback to the designer of the wind propulsion devices and to try to make the control panels more understandable. Then, of course, the same simulator setup can be used for training crew and prepare procedures and risk assessments. Good. So, a short summary of what I tried to tell here is that research efforts are really essential for reaching the climate goals of shipping. And Sweden has currently great excellence in wind propulsion for ships, and we should really use that. So we have institutes, universities, and industry working together, and with a strong support from authorities, which has been essential to develop all the tools and knowledge that we have now in Sweden. So I hope that this will continue. And we're very, very thankful for all the support we've received.
Thank you, Sofia.
Thank you.
And for those of you who didn't know, Hållbar Sjöfart is actually the business industry program that we are running at Lighthouse. Do we have any questions for Sofia? And we have a runner here. Kalle is coming. You might want to put it on. Den behöver nog startas, Kalle. Typ. Är du docent? Inte. Ah.
Nu går det. Oh. Hello, my name is Robert. I was thinking of comparing this propulsion where you use wind or rotor. As I understand, in the rotor you generate electricity and then you put it to a traditional powertrain. Is that correct? Or?
No.
So the rotor is same as a normal sail.
Yeah. So in the rotor there is an electric motor. So it requires energy to spin. And when this cylinder spins and there's a wind coming across the rotor, it will generate a force.
So there's no electricity in this. Okay.
No, you need to feed in electricity.
And I have a second question. You mentioned that you have developed a tool to optimize the usage. And you also mentioned there are several tools in other universities. Why don't you work on the same tool?
So the tool is not to optimize usage, but to assess, predict the power saving, and compare different devices.
Yeah, but you put together all the resources around research in the world. Won't you get a better tool then? That's my question.
Yeah, or maybe we get better tools if we all develop the best tool that we can and then compare and discuss pro and cons. And we are actually also running a benchmark workshop we have now 20 participants from all over the world who have their own tool, and we compute power saving for the same test cases and then come together and compare the result. So we will have the final workshop next week and compare all the results between these 20 participants. That will be very exciting.
Who will win? Your tool?
So there is no winner because we don't have any truth. There is no validation data in behind. So we will just see the differences between us.
Thank you.
Okay. Do we have any other questions? Yes.
Jonas Bostrom, thank you for a good presentation, Sofia. You mentioned yaw motion, which was very good, which was important for stability. What about roll? If you put on sails, do you become more stable or less stable?
Yeah, so of course we can have some heel from the static force. Usually for most cargo vessels that's not an issue. For some light vessels or ro-ro packs could be an issue to have some heel. But the roll motions are usually damped by the sails or rotors, so that's a positive effect.
Thank you.
Thank you, Sofia, for the presentation. My question is just technical for the slides itself. I think a lot of people is taking notes or about to take. Will you share it afterwards so we can digest some of the information?
Yeah, no problem.
If you send an email to info@lighthouse.nu, we will send, but we don't automatically send out people's presentations. And we check so all slides are okay to send out.
Thank you.
Mitt namn är Bengt-Olof Petersen. Sofia, you had a diagram showing that the wind doesn't fluctuate that much over a year or over years. Does that mean that climate change has really not influenced the, let's say, average wind forces we see on the oceans?
A good question. The numbers or the graph I showed was maybe a few years old, and if there will be some changes now in the coming years, I don't know.
Because I guess the wind, it looks like the wind speeds maybe go up.
Could be.
Okay. Are there any other questions? So I have some then. So, talking a lot about research that has been done and is ongoing, what do you see the future needs for research in this field?
Yeah, of course we are not done. There's for sure need for much more research. I could mention, now we have developed these methods for assessment of power saving and sea trial methods, but the next step is to look into the uncertainties of these methods. Another issue I would like to mention is look more into the computational methods for assessing the loads, and especially dynamic loads on the devices. This is really difficult, but if we can understand this better, I think probably the devices can be designed with less safety margin, and then they could be lighter and then more efficient. And so I think this is really the next step for the whole industry, so connecting both class societies and wind propulsion manufacturers and institutes and universities. And, yeah.
Another question. Sorry, forgot. This is a little slow. What about, I see very nice test equipment there. Is it enough? Do you think we have enough of test infrastructure in Sweden, in the world, or would there be need for anything new, and what in that case?
Yeah. I mean, our wind tunnel or our towing tank here since 1940, it cannot really be used as a wind tunnel in a very efficient way. I think new types of wind tunnels is something we should look into. The wind tunnels that exist today are designed either for automotive or aeronautics, but maybe for wind propulsion we should have maybe a new type of wind tunnels with other requirements. So here I think it would be interesting to look into if we in Sweden could come together and see if there could be a need for a custom-made wind propulsion wind tunnel.
Is that what they have in Southampton?
No, it's not really. That's more designed for yachts.
Okay. Okay. Thank you very much, Sofia.
Thank you.
And you're free to step down. And I would like to welcome our next speaker, Richard Bensov. He is a professor in marine technology at Chalmers University of Technology. And Richard's research deals with understanding what forms the key hydrodynamic features of good design in order to reduce fuel consumption, environmental impact, including noise and vibrations, lower production costs, and improved lifespan. That's a lot. And I know you work a lot with Sofia on different projects, but now you're going below the surface to talk about what is happening below. The wind is changing for ship propulsion, also below the surface. Welcome.
Thank you. So, nice to be here. It's of course, if you talk about wind propulsion, you think that, I mean, the core areas first you come to mind is, okay, what is the wind? How much wind is there? How do we capture it? What kind of devices? How much thrust does that give? And how do we then operate the vessel with respect to wind? But all sailors also know that the hydrodynamics of the sailing vessel is important for the performance. And that's what I will talk about now, going below the surface. And I will focus not on the hull design or hydrodynamics in general, but I will focus on the propulsion system. So how the hull, propeller and rudder interacts and what effects that has and the need for research and what we have done lately. So what is actually changing? Well, if we now have these savings that Sofia talked about, this means that the propeller will be unloaded. Will require less force or less thrust from the propeller. So that might change the design. But at the same point, if we now talk about motor sailing for a vessel that's normally sailing but will need to be operable in heavy weather, we have a huge range of operating conditions that this propeller or propulsion system should manage. From zero, where you're only sailing, then we need to make sure that that's as little drag as possible, to maybe operating in tough weather, where it's at heavy load. So this poses challenges for the marine propulsion system. Sofia also mentioned rudder. And if you're now sailing, you have less flow over the rudder, which means that you'll have less side force from the rudder. So that's also affects maneuverability, in addition to then you have the drift, which needs that you need to compensate with the rudder, depending on how the sail arrangement is done. So I'll talk a little bit about a few of these aspects and give some examples. Yes, scale effects. We have also. I'll also talk a little bit about. So traditionally, we know how to do a model scale experiments and do a full-scale performance prediction with a margin that's sort of comparable to the sea trial tests. But now that we have the wind and we have this unloading of the propeller and we have the rudder effects, these things might change. So we need to consider those things as well. So the first thing I'll talk about is a project we ran here with Lighthouse, where we looked at the propeller design. And the first question then is at which design point should we design the propeller for? So in this case, we're sailing with zero thrust as sort of the main idea of this vessel. But we have operation points at different thrusts. So here's the thrust, here's the probability or how much time we spend in these operating conditions. So normally maybe one operates here 90% of the time or more for a vessel. So then it's quite obvious. But if we now have this range of conditions, where should we, for what condition should we design the propeller? And here we also looked at the controllable pitch operation to cover this setting. So if we run at 100% propeller, this would be the design point in terms of thrust. Here is the dimensioning of it, and we'll operate down here. So that's sort of the baseline. If we now go motor sailing, we reduce from, I don't remember the number, but say 300 to 50 in thrust. Then we shift the curve. If we don't have a controllable pitch, we'll shift this operational curve and we end up down here. But if we then can move here with changing the pitch, we can increase the efficiency to a better point. And this becomes even more important than if we sail against the wind. Then we might run into problem being beyond the engine limit, and then the controllable pitch becomes crucial. So for this kind of vessel, I can mention we did this study with a tanker as well, with approximately 15 to 20% average wind power. And then it was perfectly fine to use the traditional fixed pitch that was already installed on that tanker. But for this case, where we have these huge variations, a controllable pitch is essential for the operation. But then to the question I said first, which design point should we then design this controllable pitch propeller for? And then we did a study where we had, these are 5 different operational conditions on the plot I showed before. And then we picked each of these as the design condition for the propeller design. And here's then for one route, this is the energy consumption in the C1 condition, in the C2, etc. And then we can see that, okay, if we design the propeller for the C2 condition, we end up with this. If we sum these, we get the total energy consumption. And we can see that there's a clear trend that if we design the propeller for the C5, the most heavy condition, we gain in total savings for this vessel. So actually, even if the C4 was the most common one, from energy perspective, that was covered also. So the experience from this test case, at least, was that, okay, we need to design for the heavy loading condition and make sure that it operates okay also in the lighter loaded conditions. So this was one experience from this sail prop project that we run within Lighthouse. Then looking at systems effect a little bit, we have recently looked at this chemical tanker. I think Klaus is here somewhere. It's happened to be a TAN tank, but it's a Kongsberg design, so we used that in our study. TAN tank was not involved in this one at this stage, at least. And we just wanted to look at the system effects of this vessel. So we assumed a wind-assisted conditions from 0 to 20%, just hypothetically, without sort of thinking about the aerodynamics of it, just to look at how the propeller works. And we looked at two different designs. So we had the original design, which is already this is a very slim, low area blade. But designing for the wind condition, we could reduce, or Kongsberg did this design, so we reduced the area even further. So how much do you then gain by changing the propeller at the same time as you change or add the wind assistance to this kind of vessel? Okay. So if we did the self-propulsion CFD, so we ran the ship. Now we didn't consider all aerodynamics effect. This was limited to hydrodynamics, so we didn't include the drift angle, for example, or variations in wind. But we ran self-propulsion in full scale with the original propeller and the new design of the propeller here. And we assumed a wind thrust from 0 addition to approximately 20% added wind. And then we can see the changes. So we can see how the RPM goes down. We can see the power savings. And what is worth noting already here, perhaps, is that even if this is 20%, we gain more in power saving than 20% because we get a better operational point from a hydrodynamic perspective. And if we then compare with the new design, we see that at standard up or at no wind assistance, we get more or less the same. But we see a trend here, and in this case, with 20%, with the new propeller, we gain something between 2.5% and 3% additional power saving. So looking at this case, we see that with 20% wind, we gain approximately 25% in power saving by also looking at the hydrodynamics effect and redesigning the propeller. This is, of course, something worth to consider. Then the interesting part comes if we look at model scale instead. So we did exactly the same thing in model scale. And then you can see the predicted savings here. So in fact, doing the same study in model scale, we don't see any additional gain from the hydrodynamics. So there's a clear scale aspect to this, that a model scale test, model scale simulation assessment will not give the same answer as if we do it in full scale. So what's going on? We don't know for the moment. But there are, of course, issues. We had to assume something. How do we translate the wind assist in? So it's easy in full scale. We know the resistance. We can assume that, okay, this amount of force or something. But to predict the wind power or wind thrust in model scale is also a challenge. And also, how should we balance? What's the propeller load? So if we do a model scale test, we add a rope force in order to get the correct propeller loading for the self-propulsion test. But how do we do that when we have wind assistance? How do we combine these? And then we have scale effects on the propeller and on the hull to consider, which we believe are even more important when we have this really low blade area propellers. There are other effects than friction that comes into play. So this is also unexplored. And there are then obviously, as we saw in the previous slide, interaction effects between these. They don't work the same in model scale as in full scale. And these are research questions that partly at least will be addressed in a new PhD project at Chalmers and Rice that is funded by Lighthouse. So these are open areas to look into. Finally then, thinking about rudder performance, I mentioned that before, that we get less side force. So if we look at the standard sort of lift, this is the lift coefficient here to the angle of attack of a foil section. We can see here that we get a linear behavior here depending on the angle of attack of the foil. But this is then the lift coefficient. So if we get the force, we need to multiply by the velocity, or the velocity comes into play here. And the velocity for a rudder, if placed behind the propeller, is governed by, you have the propeller slip. So the propeller accelerates the flow, so it controls the flow over the rudder. Which means that if we now have less propeller loading, the propeller slip will be reduced, so the velocity will be reduced, and thus the force. Even if we're at the same angle of attack and have the same lift coefficient, the actual force will be less. We'll also, with this less velocity, might run into stall problems and a bit more complicated behavior because of this lower velocity. So there are more aspects, we believe, to looking at the rudder than changing just the size of it. So this was also mentioned that at drift we always have a rudder angle. So increasing the size will increase the drag when we have low velocity or normal operation. But it will also influence increased drag for sailing at drift. So this is also an upcoming project that we're looking at propeller-rudder interaction for sailing conditions with different angles of attack and lightly loaded propellers, low slipstream, to actually figure out what goes on and in the long run see if we can improve the propeller or the rudder design for wind-assisted vessels. So I'll stop there with just acknowledgements of the different projects. We have Lighthouse, Trafikverket, Energy Agency, and Kongsberg who has supported this research for us. Thank you.
Thank you, Rickard. Do we have any questions for Rickard? Reto? No? You're on. Forgot to say, but we're streaming this, so that's why we need to use the microphones. I think it said so in the invitation.
Thanks for a nice presentation now from an operator's point of view. If you're looking at wind, how the wind is affecting the lifting force, for instance, stuff like that, have you also looked at what happens? The wind is never constant, either in speed or direction. I mean, if you have wind gusts, and a shift of wind, how is the ship behaving then? Is the rudder able to compensate for that wind shift and wind gust?
No, we have not looked at that. That's also an interesting question in how to operate the vessel and what time scales are wind gusts affecting the sails. And also, as Sophia mentioned, how much can you actually cheat? And so there's an interaction between the air and the underwater system that's also a future research area.
Thanks.
Okay. Bengt Olof has a question here. Or is somebody else down there? No?
Ja, Bengt-Olof Petersen. You mentioned the difference between full-scale and model scale evaluation. I recognize this from previous projects I've been involved in. You consider a device, you're hoping for a gain, and then you do model test, and that gain isn't there. And if you're brave enough and do the investments, very often the gain is actually there. So what is this? What does it depend on? Is it the boundary layer issues or what? I'm just curious.
Yes, you have the boundary layer from the ship, so the wake will be different into the propeller. In this case, we also have laminar turbulent transition on propeller and rudder that might be affected. So and there could be other effects. So the suction from the propeller in this case will be different on the hull, affecting the whole system. So we saw this difference here, but we don't know exactly what it depends on. So that's something we'll look more into. It seems definitely more prominent for these wind-assisted vessels than, well, on the other hand, we have 60 years of experience in doing full-scale predictions from model scale for regular vessels. So this is a new area to do more work onto.
Thank you. I have a question. You also work with underwater noise, and a big thing that the noise comes from is, of course, the propeller.
Yeah.
Have you looked into that here? Because it should be much less noisy with these propellers.
Yes, we haven't looked into it yet. But indeed, if the propeller is more lightly loaded, it should cavitate less. That's the expectation, at least. And then the noise should be reduced. But on the other hand, if you operate in areas or if you design the propeller for too light conditions and you need to operate at full, then you might have worse cavitation for those conditions. So temporarily, it might get worse. In general, it should get better.
Will this be included in the other project you're working with?
Perhaps.
Okay, we'll see.
Thank you.
Any other questions to Ricard? Thank you, then.
Thank you.
And we are actually going to have coffee now. So be back at your sitting in here, 11:30 at the latest. And enjoy. And please take your seats. So, we will now get the last presentation in the research section, and it will be given by Ulysse Domé. And Ulysse holds a Master in Science in Fluid Mechanics from École Polytechnique in Paris, France. There's a Paris in US, at least one also. And a Master of Science in Naval Architecture from KTH. And you recently defended your PhD thesis at KTH and is now a postdoc at Wallenius Marine in collaboration with KTH. And the title of your presentation is the same as for your PhD. So, very welcome.
Did that work? Do you? Okay, right. Hello, everybody. Thanks for a nice introduction. And I didn't realize when I prepared the slides that I was going after Sophia and Richard, so I could have skipped half of the introduction, so I might end up skipping some slides, but it's good because then you already know some of the things I'm going to talk about. But anyways, I wanted to start with that, because this is the future. And there I don't actually completely agree with Sophia. I think this one does have an engine, but they didn't mean to use the engine. And I do think we can get rid of this thing, which would actually simplify a lot of Ricard's problems. If we don't use the propeller, because we use the wind, no more problem, no more scaling, no more blah. We don't need to think about it, we just sail. So much simpler. And I'm sure that a lot of you don't really agree with me, but I also think that a lot of you here actually have the power to do that. If you ask me, I think we can do it. We can go back to those beautiful, slightly modernized ships that don't really need the engine. I think we can. But of course, there are still some challenges, and that's why we are doing research on it, and there are still a lot of questions. Let's see. I would just talk about those things. Little background. Most of the research that I'm going to present was done in the context of the wind power car carrier project that was started 2018, if I'm not mistaken, by Wallenius Marine in collaboration with SSPA, or RISE now, and KTH, and was funded by Trafikverket. And you might have seen this, maybe not. It's about, the aim was to make a feasible, a 200-meter something ro-ro vessel that can carry about 7,000 cars, mostly with wind. So the aim was to reduce the emissions by 90%. So we're really talking about a sailing vessel, not just sail assist. It looked like that at the beginning. You might have seen it look like that. Actually, Ricardo did. So I think you've seen all versions so far. Still the same idea, just the commercial design evolved at the same time as the research project. And then it ended up looking like, that's the latest version with new wings that I think we will hear about this afternoon. They got a little bit shorter, but a bit more efficient, so should work anyways. So most of that was done in this context. One of the biggest questions that we've tried to answer at KTH so far is, how do we control these wings, these huge wings, and the whole vessel? Because that beautiful ship that I showed at the beginning, there was a fairly large crew to do that. Can we really today have a crew sitting on the deck of this and look at 80-meter wings and trim it? Probably not, for many reasons. First, they don't really know how to do that. That's not their job. Second, just the 80-meter wing is kind of hard to look at. So you can't really do it. And it's not like a normal sailing boat where you can just sit and you would feel, okay, I trim a bit my main sail and I feel that I go faster. You won't really feel much on this huge ship. But anyway, so we need to try to control them. And there are some questions we need to answer before to be able to control them. And the first one, even though that feels obvious, we need to know the wind, because the wind is our fuel. The wind is really what we need. So one question we try to answer is how, or two questions, there are two question marks, is how is the wind profile, so vertically, how does it evolve offshore, and how much influence do we have of the vessel versus the other, yeah. That's one question. Another question that Sophia has already talked a little bit about is how are the wings interacting with each other, with the hull? This is fairly important because now again we're talking about a wind propulsion project. We need a lot of surface to generate enough thrust. If we put one, maybe two systems, it's a little bit easier, but now we really need to get the best out of that. So we need to make sure that we understand that very well. It's like when I'm on my sailing boat, I know what happens if I trim the jib and what happens if I trim the main. I have a feel for that, but now we need to find a good way for a computer to know that, not just us, people. And another aspect that is slightly different is that how do we measure things? It's actually pretty tricky. How do we measure the wind? How do we measure the aerodynamic values? Like when we talk about the lift coefficient of an airfoil, of course in a wind tunnel or in CFD it's very easy. I can say I have that much lift, I have that much thrust. In practice, in real life, how do we measure these things? How do we calculate them? Yeah, those are some questions that we need to answer to be able to answer the bigger question, how to control such wings and ship. Of course, the hydrodynamic is very important, but this is not an aspect I will talk about. We already heard some. So I'm only going to talk about wind, or what's above. And a little more background, you might think aerodynamic. Why am I talking about aerodynamics? Why did Sophia talk about that? We know a lot about aerodynamics. We have planes since a really long time. And we have a lot of data from that. But they're actually fairly different. One thing, maybe, a plane has pretty much one wing, two if we count the tail, but the tail is very small, it's very far apart, it has a different purpose, and also they are kind of small. This is a top view of an Airbus A380 that's supposedly a pretty big plane to scale with our test case. Now it doesn't look that big anymore. So yeah, we have very different. The aerodynamics is actually pretty different. The interaction effects, they don't really exist on a plane, so they don't really know that in the plane industry. We used to have biplanes or triplanes, but then again, it's only in one direction, and that was a while ago. So research-wise, we don't really have the data that we have now. So it's difficult to get to use that. So we need to know more. And there's another, maybe obvious, but another pretty big difference. A vessel like that will operate at a speed around, let's say 5 to 10 meters per second, around 10 to 20 knots, something like that, depending on the ship type. And the wind will be somewhere around 0 to, let's say maybe 30 meters per second. Otherwise, we will try to avoid anything higher than that. Which means like those numbers are pretty close to each other. A plane goes around 450, 500 knots, something like that, 230 meters per second. And it's much higher up, so it's higher wind speed, but it's maybe of the order of 50 meters per second, something like that. Which means that an airplane will always have a wind that is pretty much straight ahead. They go so fast. So, and maybe something like plus minus 10 degrees or something like that. But we, on our boats, we have wind coming from anywhere. Even in case of motor sailing, we still have a very wide range of wind directions, which means we have different aerodynamic interactions and different aerodynamic aspects. If we look, I'm not going to talk about that one very long, but if you just look at now that the wings are put at the same angle to the wind on these drawings, and you can very easily imagine that the interaction effects here and here are pretty different. The wings are in a completely different position, even though from a wind point of view they are in the same position. And then imagine a hull below that. It becomes a little bit messy and complex. Now in the title I had experimental, because now we heard a lot about CFD and it makes very nice graphs and we get a lot out of CFD, but I like real life. And especially for the first aspect, we wanted to know the wind, and maybe that feels a little that's something new. I hope it's partially something new. We know the wind very well on land because we live there, because we have things that make us that we need to know the wind. We know the wind pretty well close to land, offshore, because of the wind energy industry. We put wind farms close to land because it's still shallow enough that we can do it. But then when we go very far offshore, there is almost no measurement. There are a couple of buoys, a couple of vessels report their measurements. But except for that, we only have satellite measurements, which means we don't really know much of what's happening. So we only rely on mathematical models. And personally, I don't like that. I like to know the actual truth. So then at the beginning of the research project, we thought it was important to know the wind. So we installed a wind LiDAR. It's the little yellow thing here on a Wallenius ship. It measures the wind speed and direction at different heights, from 10 to 200 meters above the vessel. It's just a laser spinning in the air. There were no disco balls. We don't see the laser, so it's a little bit boring, but there is a laser going around there. And we get wind speed, wind direction. It's pretty cool. We put it on. In total, we managed to get 3 Atlantic crossings back and forth on 2 different ships that were like sister ships. That's a detail. But out of usable data, we have at least a month of usable data, like actual useful, let's say, data. And we can get some interesting things about it, but that's not how I organized the presentation. I forgot that. I was talking about experimental resources. Sorry about that. I keep the suspense about the wind now. You will know soon how the wind is blowing. That was my point. But then another experimental resource that we developed at KTH is a 7-meter test platform. Again, I like real life. So we thought it would be nice to have an asset, like a physical boat that we can put in water. But making a 200-meter long prototype somehow was a touch complicated and expensive, so we had to scale it down a little. So we went for 7 meter. That's more or less the same size as what SSPA uses in their towing tank, so that was easy. We had a nice partner to make that happen. It's pretty much a robot, semi-autonomous. It goes sailing like this is a real picture. It's not a it's real. We go in real life, in real condition. We try to control it, and we use it mostly for developing sensors, sensing techniques, control algorithm, control techniques. Because in real life, someone asked about scaling. Of course, scaling here, nothing is correct. We know that. The rudders are too small, the hull is too small. Maybe we managed to get the fruit scaling and the waves kind of okay if we go in nice conditions. But that's not the point. The point is we can do tests in one way and then in another way in the same conditions, and we can compare them and we can see how it behaves. And the beauty of real life is that things happen that we didn't think about. That if you set a simulation, you're gonna get the outcome of what should come from that simulation based on what you input. But when you don't know what you input, because we don't know what happens in real life, then other things happen, and that's pretty nice. Makes it difficult to process the data, but it's interesting at the end. Now, some key results. I already talked about those challenges. I'm not going to go through again. But so how is the wind profile? The first question. If we look at on the left, all the tiny gray curves are actual measurement of the wind speed from the deck or slightly above the deck up to 228 meters. What's interesting here is this is measurements from one day, I don't know, in December a few years ago. And during one day, we got pretty much the whole spectrum of how the wind profile might look like in just one day. Sometimes it was very straight, sometimes very curved, and that will affect how the performance, or that will affect the performance of a wing, of a rotor, of any ship that's going in there. Something didn't go correctly in the presentation. There were not supposed to be any numbers here, but it doesn't matter. Oh no, they're not there. Sorry. This might look a little bit weird. This is just if we put some numbers behind these shapes. One way to represent the wind is using a power law. We need an exponent a value of an exponent, and that's the distribution that we get. How often do we get wind? What's very interesting is this line, I thought I had another one, is a value of 1/7. That's what used to be, or what a lot of rules still recommend to use. The ITTC updated, now it's 1/9, so it's a bit closer to there. What's interesting is that that's pretty far from what we measured. That's a quite important aspect. What we measured is that the wind is mostly straight, or very close to be straight, which for wing would be pretty good, but it's important to know it. That's the main key takeaway. Now the other important or interesting part when we, again, for scale, here's the vessel. And if we look at the lower part of this graph now, this is not how the wind is supposed to look like. This is only the hull impacting the wind. And we can see that it goes pretty high up to at least there somewhere, like 50, 60 meters above the deck. The wind is very much perturbated. Now, during that day, the wind was mostly from one direction, so it's all in more or less the same impact. But of course, that varies with the wind direction, because the hull changes. And yeah, that's going to impact a lot our performance. I can skip that one. I think I'm talking way too much. So now I talked about the wind. How is the wind profile? How it is offshore? A little bit how to measure it. Now I talked about the LiDAR. But you could see, if I back up, any measurement we do here are wrong, pretty much. Any measurement we do on the ship is not correct. If we don't manage to measure 100 meters above, it's something else. But even if we measure 100 meters above, if I measure here, how do I know which curve I should follow right now, right here where I am, to know what the actual wind speed is at my deck level? Given that in one day it can change that much. So even just measuring the wind is something very difficult. Now I'm going to talk about the more aerodynamics. Sorry for the bad camera. That was the first time I used the drone. I'm not very good at it. The important thing was that you can see these wings interacting, and I hope you saw these telltales that things happened. They change a lot, and that's what we try to understand. And one thing is that we want to understand what's happening. So we had, on this boat, we had a lot of different sensors. So we put some pressure sensors. You don't see them. There are teeny tiny holes on the wings. So we measure the actual flow around. But then these telltales are normally used by sailors as well. So we thought, let's try to use them as a sailor would on a normal boat. So we put cameras looking at the telltales, and then we have an algorithm trying to detect whether they are attached or detached, and then we move the wings around. There you can see. So I have hours of very interesting footage of wings like that, and we see that things happen. We can measure things with that. What we get out of that is pretty curves. Don't need to talk much about it, but we move the wings around. What's interesting is with the telltales, we somehow get either the flow is nicely attached or the wings are completely stalled and we don't have as much force, and we can correlate them very well to the pressure measurement. So both techniques work. They have their pros and cons. The aim was to test different techniques and get aerodynamic data. Then out of that, we get some pretty graphs. If we look on the left, if we have all the wings at the same angle, we get some amount of lift on the aft wing and a bit more to the front. And then if we go on a beam ridge with the wind from the side, then we get pretty different values and different change. And then, as I said at the beginning, the aim was to try to control. So we want also to know how to maximize what we get out of the wings. So we tried some with the 7-meter model, just not really, it's not a proper optimization. We just try different strategies, sheeting the wings a little bit differently, gradually. And we can see that we can get much higher force in total. Maybe a bit more on some, a bit less on some, but globally we can improve that. Both upwind and beam ridge, but now I didn't put the angles, but the angles are actually quite different to get this lift. Now I talked about how the wings are interacting and a little bit how to measure them. And then at the end, and then I'm going to conclude, I don't even know how long I've been talking. When we have all this, what we can do now and in further also, we put all that, we have better tools to know, we know the wind, we know their interactions, we can put all that in a velocity prediction program, the one from SSPA or another one. It's good to have different ways of calculating. We can put them in a time domain simulator so we can then simulate something that should be as close as possible to reality. Then on top of that, we can do, once we have that, we can do weather routing. And once we do all that, then we can try, even on the scale of a whole weather route, like a whole route, did we gain that much by trying to move the sails all the time? Or does it not matter? Should I just let them stall? Do I really need to get that gradual trimming? We can test all that from measurement to actual testing in a longer route. I think that was actually a pretty good conclusion. But yeah, the wind profile is globally more straight than we thought, at least. The hard influence is maybe even larger than expected instead. It is difficult to measure the wind, so that's why also Sofia talked about one project that we have now starting. We try other techniques, other ways to do that. The wing interaction is very important, and the hull, of course, is important. But if we trim, if we do put some focus on how to use that, maybe, like if we don't do anything, it's pretty detrimental, like we lose quite a bit of performance with wing interaction. But if we know it, and if we think about it, we can actually use it. We talked a little bit about yaw control earlier. Because we have these interactions and because we have so many wings, we can actually work on that also. Maybe those, so the objectives need to be slightly different than what we would think first, but we can maybe sacrifice a little bit lift on one wing and then instead the rudder becomes more straight, and that's all nice and good. We can do all that. And we have a nice test platform to test this at KDH. Thank you for your attention.
Thank you very much, and you were just on time, so perfect. And do we have any questions for Liz? Bengt-Olof?
Yes, as you referred to when you are sailing, you are hoisting your main, which may be quite big. You have a certain speed, and then you hoist quite a small jib, and you notice that your speed will increase substantially because they are working together, the main and the jib. Here it seems you view the four sails as four independent sails. Isn't it possible to put them more close together so they actually work together as one system?
That's a very good question. Yes and no. We need to find a balance. If we put them closer together, then they do work a bit more in some angles. And then at some others, that's going to be worse. If we put them further apart, then they are more independent, so we don't have as much dependence on where the wind comes from. But typically, very early on in the project, we had also looked at what if instead of having four wings in a line, we put like 2 and 2. And then typically on the beam reach, then the two wings end up very close to each other, and that they work exactly like a main and a jib, but only on the beam reach. And then when we're more upwind, then it's not the case. So there is the problem. Ideally, we should be able to shift the wings around as we sail, so we can always make the best of it. That's going to be a touch complex, and I'm not sure anyone will want to do these developments. But
okay. What is your research project now at Wallenius as a postdoc? Is continued the same work? Or?
Yeah, pretty much continue that. Now that we have a lot of bricks on how to do this vessel control or wing trimming strategies. So now the aim is more to work on really algorithm on how to make the best use of the wings, how to make the best use of the boat, the whole vessel, both in like more fundamental ways. So we have planned experiments in a wind tunnel, but also in practice, how do we do it in practice? Continue this.
Okay. Any other questions?
Yes, please.
Yeah.
Am I heard? Yeah. I'm Lars Fjälldal of Sjösportskolan. I'm also a sailor in racing sailors at some times. And I'm wonder if you are considering the shear of the wind while it's twisting like this. So when you are sailing on a starboard tack or a port tack, you have different twists on the sail. The further up you get, and also for the sail, the square rigger you had on the picture, the belem, you also adjust the sails, the yards, to different angles. But here you don't seem to have different angles of the sails.
No, that's a very good question. Also, when we had these 80-meter big wings, then it's difficult. We very early on we thought, okay, do we need to split them so we can do that? Then it's a matter of how much really there is. One good thing, if we have a more straight wind profile, as it seems to be, is that means less twist. Like when we sail on small boats, we're very close to the surface. There is a lot of shear, so we have twist. But when we go a bit higher up, maybe if the profile is straighter, then it doesn't twist as much, which is good because then we don't need to think about that. And then now I only showed the wind speed on the hull, but of course the wing angle is also affected a lot by the hull, and that I think is actually more important than the natural twist of the wind. In some condition, we measured the wind shifting 10-15 degrees within 15 meters above the deck. That I think will have more impact than the pure twist of the wind. And then, I mean, maybe we will hear about that more this afternoon, but I think from a technological point of view, that would be pretty tricky to twist these rigid wings.
Yeah, sometimes you can do it with some automatic flex or something. But also you have the situation is different on the southern hemisphere compared to the northern hemisphere. The shear is in the other direction.
Difficult.
But you know that.
It's, yeah. There is a lot of aspects, but at the end I think it's not going to be that big a problem. Okay. We are lucky the wind is actually more straight in the Atlantic at least.
Thank you very much.
Thank you. And the last question before
maybe a strange question, but I'm not like questioning your expertise or anything like that. But you talked a lot about sails and sailing and this and that, and you seem to be sailing yourself. And if I'm thinking about sailing and advanced sailing, it's kind of America's Cup and these guys. Have you had any cooperation with them, exchange of expertise or anything like that? Because I feel that these guys are at the forefront regarding anything regarding sales. And
that is very true. They are quite far in many aspects. Me personally, no, I have not had many contacts. I know that at Rise maybe a bit, or some at least have contacts. One thing is that globally people in the Cup, or if we talk about the Cup, they don't really want to share anything. They are very good at what they do, but they're very good at doing it on their own. I think even more now with the previous Cups, there used to be a lot more involvement from research institutes or universities because they could do testing, and now they're not allowed to do wind tunnel tests. It's only CFD, and then most teams are pretty much on their own. But if you do have contacts and if you have ways to, I think that would be a good idea because yes, there are people who know a lot.
Unfortunately, I don't.
Okay, thank you very much.
Thank you.
And now to our last speaker before lunch. Rules and regulations is something that is also quite important. And the next presentation will be given by Mikael Johansson. He's head of DNV Maritime Advisory Sweden and Denmark, and has worked at DNV for 20 years, more than 20 years, working with qualification of new and novel technology in the oil and gas and shipping industry. And among those projects, you actually have some hands-on experience as risk and test manager for wind projects. So, welcome, Mikael.
Thank you very much. Thank you. Yeah, Mikael Johansson, and obviously being my age, I was super exciting talking about WASP. That sounds great, but then I realized it was not Blackie Lawless, and I want to be somebody, so we leave that and talk about wind propulsion instead. And I will try to give some overview of how we work in DNV and projects that we have done in this domain. Yeah. So starting off, hopefully and maybe many of you know DNV and what we are doing. We celebrate 160 years this year, so that's nice. Of course, the origin of the company is related to the maritime industry, and we will get back to that a wee bit later. I think also important to mention is that around 5% of our revenue is allocated to research and development. Much of the stuff that I'm going to talk about here today is obviously founded upon that research, and we are releasing a lot of different information throughout the years, and there is quite some articles to be found related to wind-assisted propulsion in the research that we do. So it's freely available if you want to read more and have more insight and also our experience related to wind-assisted propulsion. But if we get to it, why are we talking about this at all? Well, basically we're talking about this because the shipping industry needs to decarbonize by 2050. That is the target that we have set for ourselves. With that light, more advanced and more costly energy efficiency devices are currently in play compared to where we were, so let's say 10 years back, right? And that is why we are now talking about more advanced and more costly aspects like wind-assisted propulsion, hull lubrication, aspects that have been tested and investigated, but has not been sort of on a large-scale breakthrough in the industry. But with the ambitions that we have, and with that we are now putting also a cost towards emission, it will be a new environment for us. And that is why we also talk about wind, and what can that do for us. We are in the very early phases of, let's say, then the new wind era or the second wind era. There are some ships out there, both with different types of wind solutions, rotor sails, hard sails, suction sails, etc. We've seen these pictures before. I guess we will see more of them throughout the day as well. Sofia was talking about the various types of sails. I think it's also fair to say that when we talk about sail solutions from our perspective, we are not only talking about the hard sail solution that Ulysses was talking about earlier on. We have the rotor sails, we have the soft sails, we can even talk about kites. So everything that we use to utilize the wind to propel our ship is basically what we address when we talk about sail solutions. Going back to that previous picture where we say that if we do as much as we can do when it comes to the energy efficiency, maybe we can reduce the amount of energy that the shipping industry on a global basis consumes up to, let's say, 16%. How much of this can come from sails? We've heard some different arguments here already during the day. Is sails for everyone? Well, I think we share the opinion of Sofia. Well, for all shipping segments, sail will not be the solution because of trade reasons or because of the ship itself, right? For example, having sails on a cruise ship, I think they will have challenges with that, and they need to take away the roller coaster instead, and they don't want to do that. So that's just the way it is. But can sales have a benefit for the shipping industry. And this is a very simplified calculation and overview. I think Sofia showed more and more in-depth calculations of that, showing quite high numbers. But also from our point of view, yes, for certain ship segments in certain trades, there are significant benefits to be gained. We are seeing here some 19% and onwards. And of course, these are huge numbers. So when building a ship today, if there is room for fitting a sail solution, it should always be evaluated. I think that's the conclusion from our end. Also, as Sofia was mentioning, there is a lot of these various sort of estimation calculation tools that you can find, both that has been developed and as far as I'm aware, you can also find them freely available on the World Wide Web for the ones who want to test their design and what a sail solution might do for them in their trade and their type of ship. But there is definitely a case for wind as we move forwards towards 2050. Slightly updated numbers compared to Sofia's. I think there has been no major revolution. This has been slow development, but increasing. The blue or dark blue, if we look at the different type of technologies, are the ones that we have sailing as per today. The light blue is what we have in the order book. And obviously, as you can see, sort of the new kid on the block is suction sails that has gained more market shares in the order book than the rotor sails that so far has been the dominant sail solution. If we look at which ships then are suitable for a wind propulsion system, we see that it's quite even spread along quite many different types of shipping segments. But that bulk carriers maybe stand out and is advancing a bit further than the rest of the different type of ships. And of course, this has as we talked about, it has a trade aspect, and it has a where can we fit the wings aspect, where bulk carriers are maybe one of the more favorable ship designs that we can look at. Good. So that was a bit of the background. What about the rules and regulations parts then? Well, the whole reason that we are talking about sails here today is, as we talked about, the decarbonization objectives that we have as an industry. Basically, as per today, we are looking at two measures or two regulatory requirements that manages this aspect. We have the EEDI, Energy Efficiency Design Index, that was introduced quite some years ago, which forces new build ships to be more energy efficient as we move along. Obviously, there are many things that we can introduce to make our ships more energy efficient, but there is the innovative technology part where sails come under, which will have an impact on the EEDI measure. And this is sort of ticket to trade. You need to comply with your EEDI. If you don't, then you're not allowed to sail. And of course, as we are emptying out other more easy energy efficiency measures, of course, wind and other solutions will become more and more attractive in the new build market. So that's one aspect from a regulatory side where wind has a definite factor. The other measure that we look at when it comes to the decarbonization aspect is the CII, the carbon intensity indicator, that is measuring the operational efficiency of our ships or ships in the fleet. Quite easy. How much fuel do I consume? How much emissions does that generate? How much work have I done? Obviously, if I introduce a ship, or if I introduce wind propulsion on a ship and can reduce my fuel consumption by 20-ish% or 40-ish% or whatever numbers that has been bounced here today, that will have a huge impact on my CII rating. The same regime here. The CII rating is under discussion, but the projection is that that will also be a gradual decline towards zero at 2050. So of course, introducing wind-assisted solutions and reduce my fuel consumption and hence my emissions will help me to reach the acceptable target levels for CII as we move on. I think those were the two overarching rules and regulations parts, and basically the main drivers for us being in this room here today. Moving on, I talked in the beginning that DNV was 160 years old. We started out with rules and regulations for wind-assisted propulsion. That is what we were doing at that point in time. We are still maintaining those rules, so we have a few ships that have sails that are in class. Among them, Göteborg, in some direction from here, that are in DNV class, based on the tall ship rigs notation. So we have worked with this from a DNV point of view for quite some time. Obviously, what we are talking about now is maybe a bit of a different ball game, right? So we developed rules for the new type of sail solutions or WAP solutions. They were released, I think it was in 1819, and continuously updated. We have heard many times today that this is a moving target. We're gaining more and more experience as we have more and more ships installing these types of solutions. So I think you can expect that these rules and regulation will develop quite significantly over time as well. The rules that we have are basically split in two parts. If I am a ship operator, I want to look at this. I want to have the WAPs or ship WAPs notation on my vessel. That is what I need to do. So then I need to look at that kind of rule set to make sure that the ship is fit for integration of wind-assisted propulsion. And it's a number of aspects that needs to be addressed. I don't think this is the forum for classification systematics, but it follows the similar standard as other classification regimes. If I am the manufacturer, we look at this, the wind-assisted propulsion system standard. Again, not diving into class systematics, but basically how we are working with this and how we're working with manufacturers is basically that you can have an approval in principle, saying that we have a certain type of design, and we assess that this is a feasible technical solution to be implemented on a ship. Then you can make that more and more detailed. You can have a type approval design or type approval design approval. Very strange wording. It should be type design certificate. Or you can have a type approval, which is more detailed. We will get back to that later on, based on this sort of requirements. So what we have done is to ensure that these solutions are safe, develop both rules and regulations for the ship operator, as well as rules and regulations for the equipment manufacturer or the supplier of the equipment. Again, as this is new technology and as also classification rules are moving more and more over from prescriptive to more risk-based approaches, much of the focus when it comes to how we have developed the rules for wind-assisted propulsion is based on the risk assessment that is put upon the either supplier or the ship operator. So that is the starting point in both those types or both the rules and regulations that we have developed. The first phase that we often look at is the approval in principle aspect, making sure that in an early stage of development, the technology is feasible from a rules and regulations perspective. And then you can develop that into more detailed assessment when it comes to the TADC, Type Approval Design Certificate, or type approval, which is more stringent and more have more requirements in them. But it all starts out with, have we identified the risks in relation to our design and how that will affect the ship where we intend to install the equipment. So what are we to cover then in a risk assessment? How do we know I want to design a new technical solutions? Well, it's quite a number of factors that needs to go into the risk assessment in order to make sure that this is safe and reliable for the ship crew. So we need to take into account all the various operation modes of the ship and the sail, and how it will interact with other systems in relation to, or how the ship's or sail solution will interact with other ship systems. And as again, we're talking about new and novel technology here. It's a lot of unknowns, it's a lot of uncertainties, and it's a lot of technology that are developed bespoke. As Åsa was mentioning, I've been involved in one such project, having the responsibility for the risk assessment. Blurry picture in the middle, but that's how it is. We were following the technology qualification regime when we were doing this work. We were looking at quite a number of risk. I think through various HACCP and FMECA works continuously during the development of the technology, we ended up with several hundred different risk items that needed to be managed somehow or another. In some cases, of course, we needed to implement design changes or measures that to improve the design and reduce the risks. In other cases, we needed to include different types of testing to make sure that these risks were managed. These several hundred risk items were then boiled down into a test program that were done sort of throughout the development and installation of this sail solution. So it's of course nice with prescriptive rules. The rules that we have currently are not as prescriptive. They are more based on making sure that we are able to demonstrate that we have identified and managed the risks and that we can prove that we're closing those out in various kinds of tests throughout the development. Going back a little bit to how do we get our equipment certified? How can we make sure that we can put this on board our ship? For a manufacturer that wants an approval in principle or a TADC, there is basically no survey. We need to demonstrate documentation and documentation only. If you want a type approval or a product approval, there are more stringent requirements. There are assessment of production, there is surveys, etc. And of course, if you want to have the VAPS notation, then you have the quayside testing as well as demonstrating the performance in sea trial, as was highlighted by Sofia earlier on today. So that is what you need to do in order to be in compliance with the rules and regulations that we currently have. So what we are doing in DNV, obviously we have the classification colleagues that are doing the work that I have now described from a regulatory point of view, providing the AIPs or TADCs or whatever is needed from a rules and regulations point of view. What we are doing in advisory is trying to support both suppliers as well as ship operators with very much the same topics that has been discussed earlier on today. What would be the best solution in our type of trade for our type of ship? Making sure that risk assessments are carried out and documented and closed out throughout. Of course, what many are looking at now is sort of wind-assisted propulsion. Yes, it's on the table. When do we need to or have to start thinking about it from an EDI or not EDI but CII perspective, so to say? So supporting in those decision making as well. Good. The intention was today to have a bit broader view than only talk about what DNV is doing. That failed dramatically. But the other classification societies are, of course, active in this field as well, working with similar topics. And if you look at all of the big ones, they have similarly developed rules and regulations and points of view when it comes to wind-assisted propulsion and have their opinions on this as well. So as always, sort of, it's nice to be able to talk about what we in DNV is doing. Others are doing stuff as well. Triangulation is always a good starting point. So please have a look at that also. Good. Thank you guys.
You have a conclusion.
Yeah. We can skip that. We talked about that.
Or you can leave it on for questions.
I can leave it on.
Yeah. Thank you very much. And do we have any... And I could say we also wanted to have the Swedish Transport Agency here today. And they could unfortunately not come either.
No,
So
failed dramatically.
yeah. We're happy to have you here. Or you didn't have a choice.
No. Exactly.
Do we have any questions for Mikael? Yes. Lots.
Matthias Kindberg. Do you know how the Fuel EU regulation and sales work together with the efficiency measures that's coming in the coming years?
I should have known. I don't. I need to get back on that. I published that on the... there is a measure. Someone else might know. I'll look into it and get back to it. My bad. Sorry.
Connor from Furstenberg Maritime Advisory. Looking at the whole regulatory picture, so you have classification societies getting involved with class rules, you have drivers from EDI and CII, you have whatever might be connected to Fuel EU Maritime, and can you just mention again what's going on at the IMO from the point of view of that regulatory side?
There is no, as far as I'm aware, I can look into that further on as well. But if there are harmonized rules in Ajax, that would be on IMO perspective, it would be the decarb topic, right? What you could foresee, but I'm not aware of it, is that you have harmonized rules related to certain technology from Ajax, which is the Association of Classification Societies. I'm not aware of such development, but obviously a lot of homework for me on this presentation, so I'll look into that as well.
I'm thinking more about the safety side, so effect on freeboard and load line or any of those.
Not that I'm aware, no.
Bengt-Olof Petersen. If you go back 100 plus years and you had a total loss of a sailing ship at sea at heavy weather, it's believed it's very often cargo shipped and then the sailing vessel lost its stability. So in the risk assessment, is that an issue on these kind of vessels, or is there so big stability that even if you have a squall or very heavy weather, there's no risk that you could have cargo shift and or lose your stability?
In my view, that needs to go into your risk assessment. You need to assess how is the wing solution or the wind solution going to affect the stability of the vessel, and of course the securing of the cargo. So that needs to go into that, and also sort of course, this, as was highlighted by Ulysses, this is a big thing. They weigh a lot. They are quite high. It's a lot of new forces on the ship. It's not something you install without redoing the entire stability calculations, etc., and address it in the risk assessment. So it's an inherent part of that work, for sure. But of course, that can have significant impact. I think also that relates to the question earlier on sort of gust effects, or also your question earlier on sort of how is wind developing in an era of climate change and sort of freak wind accelerations, etc. So it's a lot of things to address in that comment. But it's now governed under the risk assessment part, so to say. I don't know if that was an answer, but an attempt.
Yeah, but how does it look? Is the margins better on a modern ship with these kind of sails compared to the old bark ship, or you don't have? Maybe Sofia knows.
I think maybe you know better than I do, but in my view, obviously, we know much more about these type of events and scenarios, and new type of cargo is managed in a different way today than they were at that point in time. We don't have these huge massive cargo holds where you could have cargo shift like the grain sailors, right?
Jonas Boström, thank you for a good presentation. Making classification work exciting is not an easy task.
I do my best.
We talk about WASP. I'm wondering if we are to put a wind turbine on a ship, would the same rules apply here, or could we apply those rules that you have as a recommendation, or what would this change be?
It depends on the size of the wind turbine. I know that there are companies, and also companies represented here today, that have tried wind turbines in smaller scale. Obviously, if we put the sort of large wind turbine on board, I don't know which sort of rule set that will be applicable. But on a moving ship, I think that will be a bit of challenge to get some sort of effect out of it. I'm sure our research friends can answer that much better than I can, but you will have a lot of strange phenomena trying to do that.
Okay. Thank you. You have a lot of homework, you said.
Yeah, that's good.
So
you have to learn, right?
Thank you anyway. Thank you very much.
Thank you.
And we actually have an extra topic before lunch. So I will give the floor to Anna Pulik at Skandinaus. Very short.
Yes, just 2 minutes. Hello, everyone. I'm Anna Pulic. I work for Skandinaus. But today I'm not here to talk about alternative fuels and methanol that I hope you sometime heard from Skandinaus before. I'm here as a naval architect. So if you have studied naval architecture at Chalmers, or are you studying currently, can you raise a hand? Or if you're a TA? You see, naval architecture is our common denominator, and we have a union that is actually very active in trying to connect alumni and current students and try to pick up on topics throughout the year. So if you are not informed about these events already through emails that I send, please reach out and I will put you on the email list. We have Christmas dinner coming in like next week, I think. And after that, we have SS Martha nights, but also visiting companies with students, with alumni, and so on. So please, I'm here till the end of the day. Reach out. Right, that's it.
Thank you.
Thank you.
And thank you very much, all of you speakers and the audience. You may now go for lunch. And be back at 13:20 sharp.
Är de så stabila, de flesta lastfartyg?
Ja.